Right? So stoichiometry. Right? We talked about looking at masses. We talked about balancing chemical equations. Why do we do that? Right? The reason why we do balanced chemical equations is so that we can do stoichiometry. It's the relative proportions in which elements form compounds or in which substances react. Right? So we've got this massive compound A that we might be starting with. We can figure out how many moles of compound A we've got. We use our mole ratio that comes from our balanced chemical equation to tell us if I've got so many moles of A to start with, how many moles of B will I end up with, right? So our balanced chemical equation becomes its own conversion factor. Right? And it's going to give us the ratio of A to B to C to D. So from this balanced chemical equation, if I know how much B I've got, I can figure out how much A I would need, how much C I would make, and how much D I would make. So if I've got any one of these four things in my balanced equation, I know the ratio in which it's going to react to any of the other three. So once I know how much A I've got in terms of moles, I can figure out how many moles of B I've got, and then I can translate that into using our molar mass, which is another conversion factor, or another ratio, into the mass of B. Or I could figure out the moles of C that I would need, and the mass of C that I would produce, or the moles of D that I would make, and using its molar mass as a conversion factor, the grams of D that I would make. So I can go through and convert between all of these things, but I need this balanced chemical equation to go from one type of molecule to another type of molecule. Once I got the moles, then I can figure out grams, I can figure out concentration, I can figure out volume, I can figure out pressure, I can figure out number of atoms. But to go between one substance and another substance, I need that BCE, that balanced chemical equation. Okay? Let's look at an exercise. Aqueous solutions of sodium hypochlorite and AOCl, best known as household bleach, are prepared by the reaction of sodium hydroxide with chlorine gas. You can undo this reaction, kids, by combining that with certain other household products. So please read your warning labels on your household products. Right? I'm not telling you how to make chlorine gas because that's bad for you, but be aware that you can accidentally make chlorine gas from bleach. Right? So be careful with your bleach. So we're going to take our sodium hydroxide, 2 of those, our chlorine gas, 1 of those, and we're going to make sodium hypochlorite, sodium chloride, and water. How many grams of sodium hydroxide are going to be needed to react with 25 grams of chlorine gas? Right? So we want to know how many grams over here of this guy, I want grams of this, are going to react with a certain number of grams over here. All right, so when you do this, coming up with a plan can be very, very, very helpful. All right, so in our plan, we're going to take our grams of chlorine. We'll convert that into moles of chlorine, and we'll do that using our molecular mass. Right, moles of chlorine. From our moles of chlorine, we'll use the balanced chemical equation to figure out the number of moles of sodium hydroxide we would have. And then from our molar mass again, for the molar mass of sodium hydroxide, we would figure out the grams of sodium hydroxide, right? So coming up with a plan like this is very helpful, right? So we're going to do grams of A into moles of A, from moles of A into moles of B, and then from moles of B into grams of B. Right? So that is our plan. So when I'm doing this kind of problem, I'm basically going to set up a grid based on this balanced chemical equation. Okay, so in my grid, I'm going to make a couple of different levels. Right, top to bottom, I'm going to make up some rows that are going to represent moles and grams. All right, so I'll put grams on the top, and then because I've got a little bit more variety in terms of the moles, I'm going to make a number of different levels that relate to the moles of reactants and products that I'm working with. So here I've got grams on the top. I'm going to have one row. I'll make another row for moles. I'm then going to start filling in the things that I already know. I know that I've started out with 25 grams of chlorine. And for my 25 grams of chlorine, I can drop that down to the mole level using my molar mass of chlorine. And chlorine's molar mass, I'm going to use 70.9 grams per mole because this is Cl2, which is going to give 0.352 moles of chlorine. Once I'm here, I can figure out the moles of any of the other things on here. And it's just whether or not it's going to be useful or not that determines whether or not I'm going to bother with that calculation. So if I look between, say, our chlorine and our sodium perchlorate, our bleach, our balanced chemical equation says that's a 1-to-1 ratio, so I'll still have 0.352 moles of sodium chloride. Same thing will happen with all these other guys. Once I know that this 0.352 moles of chlorine gas, it's a 1-to-1 ratio with sodium chloride, so I'll have 0.352 moles over here, and if I go over here, all the way over to the water, it's still a 1-to-1 ratio, which means I'll have 0.352. What's more useful for me, and what the question is asking, is going the other way. If I've got 0.352 moles of chlorine gas, how many moles of the hydroxide am I going to need? Well, that would go this way, and I can figure that out from looking at my balanced chemical equation that says I've got, for every 1 chlorine, I'm going to have 2 sodium hydroxides. That's a 1-to-2 ratio, so I'll have 0.705 moles of my sodium hydroxide. Once I've got my 0.705 moles of sodium hydroxide, I can then flip back up to the top to the gram level of looking at things, and I'm going to multiply that by the molar mass of the sodium hydroxide, which is 40 grams per mole, and that's going to 28.2 grams of sodium hydroxide. And if you want to, you can go through and draw this guy out where every time I'm breaking something up and I'm looking at an individual component or an individual molecule, right? I've got 2 different levels. One is working on the gram on the gram level up top. One is working on the mole level underneath. We've got multiple moles down here because when we start doing limiting reactant type of problems, we might be using some of these instead of, like, I got 25 grams here of the chlorine. Well, what if I started out with 50 grams of sodium hydroxide? And then I would figure out, well, how many moles of this do I have and how many moles of the bleach and the sodium chloride and the water can I make? So, we want grams. I'm going to do it. That's how I'm doing it. Right? You don't have to do it this way. If you got a better slick Rick way to do it, I'm going to do it my way. Maybe it's the Morty way. I don't know. But it keeps it straight in my head as to what's going on. Right? I can go from grams to moles using a molar mass. Right? I'm going to go down by dividing. Right? Dividing goes down. Multiplying moves up. And I can go left to right using my balanced chemical equation, and I'm going to write out those balanced chemical equation ratios, those coefficients, out here for each one to tell me, well, how many moles did I start with of my chlorine? How many moles do I end up with here? And you can see, like, once I get one of these things, right, I got my balanced chemical equation, I know how many moles of chlorine I've got, I know the moles of all the other things. Right? And if I wanted to, I could figure this guy's grams out, and I could figure this guy's grams out, and I could figure this guy's grams out by using the respective molar masses. Right? So I like Mr. Table. Keeps things straight in my head. I am not a smart man. It keeps things straight for me and organized and all together, and it makes it real easy to see if I've gone and messed something up, right? So if I'm looking from here to here, right, and I know I got 2 over here and 1 over here, and I wrote my ratio the wrong way around, I know I should end up with more over here, more moles over here than moles over here. And if you look at the masses, right, masses can be tricky and deceiving because the molar masses are dependent on what atoms are in there. Right, so my chlorine, 2 big heavy atoms, is about 70 grams per mole. Right, my sodium hydroxide, even though there's twice as many sodium hydroxides, because my sodium is light, my oxygen is relatively light, my hydrogen is super light, is only 40 grams per mole. It's about the same mass, even though I got twice as much sodium hydroxide as chlorine. All right, so let's look at some more principles. So let's look at the number. Consider the following reaction between propane and oxygen. We've got C3H8 and 5 O2s. Like as soon as I see this 5 over here, I know I'm already dealing with a balanced chemical reaction. If you are looking at your alkanes or your simple hydrocarbons like this, your odd guys are going to start off with an odd coefficient over here and have an odd number of oxygens. If you get into something like C2 or C4, you're going to have, boom. If you get into C6, you're going to have an even coefficient. You're going to multiply this guy by 2, and you'll have some sort of even number in here. Per tip, just kind of recognizing those guys as balanced. Consider the following reaction between propane and oxygen. I got C3H8, 5 oxygens, it's going to give me 3 carbon dioxides and 4 waters. Calculate the number of moles of propane present in 96.1 grams. That's the molar mass of propane is 44.1. You just take your 96.1 grams of propane, and then you're going to use the molar mass. So 44.1 grams in 1 mole. Your moles will cancel each other out. Sorry, your grams will cancel each other out. You're going to be left with moles of propane. If you want to construct a mole ratio, you're looking at the inside here. There's an implied 1. So for every one propane, right, you're going to have 5 oxygens. Right, so that's a conversion factor or a mole ratio. To calculate the number of moles of oxygen needed, you're just going to take your moles of propane. You're going to use that mole-to-mole ratio that came from your balanced chemical equation, and you're just going to multiply that. Moles of propane cancel out. You're left with moles of oxygen, 10.9 moles of oxygen. Convert those moles of oxygen into grams. 10 moles of oxygen times the molar mass of oxygen, O2. Keep in mind this guy's O2. And your moles of O2 cancel each other out. You're left with 349 grams. This is why when they talk about cars and pollution and how many tons of stuff are produced on the other side of a power plant when you're burning a fossil fuel, it seems like a lot of stuff, and it is, right? Because you are taking something that's like a carbon and a hydrogen, and you're reacting it with an oxygen, and then you're going to form CO2 and H2O. Oops, H2O. So you're pulling in these oxygen atoms, right? Those oxygens each weigh 16 grams per mole, right? So for every carbon, you're combining it with an extra 32 grams per mole. And for every hydrogen, you're adding an extra 16. So every 2 hydrogens, you're adding a 16. So the amount of stuff that is coming out of the tailpipe of your car in terms of mass of CO2 is pretty big because these oxygens are heavy and you're pulling in 2 of them. So you're going to need 349 grams of oxygen to burn your 91.6 grams of propane. Right, so you're pulling a lot more oxygen from the atmosphere during this process than you think you might be. Okay. So in order to determine the mass of carbon dioxide produced, the conversion factor between the moles of propane and the moles of carbon dioxide is required. And that's a 3-to-1 ratio. So 3 moles of CO2 per mole of propane. So our conversion factor, we got 2.89. We're going to use this 3-to-1 conversion factor here. Moles of propane cancel out. We're left with moles of CO2, 6.52 moles of CO2. Okay. If we want to convert that to mass, we'll take our 6.54 moles of CO2, multiply by the 44.0 grams of carbon dioxide per mole, moles of CO2 cancel out, 288 grams of CO2. So our small amount, right, our very small amount of 96 grams of propane is going to be converted into 288 grams of carbon dioxide, right? So you end up sticking those oxygens on. It's a really heavy process. Now, there is a way you can actually do this and get at this answer using molecular mass ratios directly. It's just really hard to explain it, and they used to do that back in the 1970s, before I got to college even, so 60s and 70s. And it works. It's just very counterintuitive to do that. So this way here, where you go from mass into moles, look at the balanced chemical equation, go from moles of one thing into moles of the other thing, and then go back into grams. It takes you like an extra 1 step, 2 steps tops, but it gets you the right answer almost as fast without a lot of the confusion that went with using mass ratios directly. And you're more confident about your answer because you can really see what's happening in each of those steps. Right? So let's do some more stoichiometric calculations, right? So our summary is step 0, not even step 1, step 0, balance chemical equation. What's it going to be? Step 0 is going to be your BCE, right? If you know nothing else, balance that chemical equation. You need it. Convert the known mass of the reactant or product to the moles of the substance. Use the BCE to approximate the mole ratios. All right. Figure out what your mole ratios are. Then use those ratios to calculate the number of moles of desired reactant or product. Right. You could compare moles of product to moles of product. You can compare moles of reactant to moles of product. That's usually what you do, but you could do moles of product to figure out moles of reactant. You could do moles of reactant to figure out moles of the other reactant. Right? That BCE works all the ways. It does not care. Right? Convert back to from moles back to grams if required to by the problem. Right? Check to see that you're not going and doing extra work on yourself if you just need to stop at moles. All right, so start with your balanced chemical equation. Find that ratio. Right? Once you've got that ratio of moles of things you started with and moles of things that you know, right? Use that mole ratio to convert. Right? You may need to convert your mass of known stuff to moles, and then moles of known substance. You do that conversion to moles of your undesired substance, and then if you have to, use your molecular mass to convert that into grams. Right? Let's look at an example. Sodium lithium hydroxide is used in space vehicles to remove exhaled carbon dioxide from the living environment by forming solid lithium carbonate and liquid water. This is a CO2 scrubber, right? You will see that in like oxygen rebreathers if you're a diver, right? What mass of gaseous carbon dioxide can be absorbed by 1 kilogram of lithium hydroxide, right? So we got 1 kilogram. Is this in our intuitive units? No. First thing you're probably going to need to do is make that guy into 1,000 grams. So that's another implied like step that you got to do, right? So step 0 is going to be our balanced chemical equation. They're going to go through and set this up for us one step at a time. So objective, we're going to find the mass of the CO2, right? We got to find our chemical reaction. So lithium hydroxide, LiOH solid, is going to combine with carbon dioxide to give us Li2CO3 and water. Right? We've got 1 kilogram of this stuff. Right? We need the balanced chemical equation for the reaction, and then we're going to need to convert our 1 kilogram of lithium hydroxide into moles of lithium hydroxide. So step 0, right? Step 0. Balanced chemical equation. 2 lithium hydroxides plus a carbon dioxide is going to give us lithium 2 because we've got 2 lithiums, carbonate, and because this carbonate complex or polyatomic ion is going to have a -2 charge, and we're going to form some water. Determine the moles of lithium hydroxide. You got your 6.94 plus 16 plus 1. That's a lithium, oxygen, and hydrogen gives us 23.95 grams per mole. We got 1 kilogram. We convert that kilograms, 1,000 grams per kilogram. Now we're going to give our grams of lithium hydroxide. We'll cancel those grams out. We got 1 mole of lithium hydroxide per 23.95 grams, which gives us 41.8 moles of lithium hydroxide. Okay. Lithium hydroxide. Lithium is a very, very light element, which is why when you see a lot of batteries and you're concerned about charge density as being one of the main factors in what makes something an attractive battery, right? It's, you don't want to do a mercury battery or a mercury cadmium battery, other than the health and recycling concerns, because 1 mole of charge on cadmium is still the same amount of charge on 1 mole of charge on lithium. It's just that lithium battery is going to be a heck of a lot lighter. One of the things I did in my postdoc was we were working with one of the Army programs to develop a continuous monitor for blood lactate and glucose. And, the guys who were the field guys, their first question is, how heavy is that battery? Because if you're carrying, you can have the most high-tech force ever, but if people are going to start dropping stuff and gear because they got a bunch of heavy dead batteries on them, it does nobody any good. It's practically useless. So lithium, very charge dense, very light. So that's why lithium shows up in these batteries. So you get 48 moles. It's a lot of moles for a very little amount of mass. Right. Step 3 is determine the mole ratio between the carbon dioxide and the lithium hydroxide. From our balanced chemical equation, we said that was a 1:2 ratio. That means that if we've got 48 moles of lithium in a 1:2 ratio, we've got 20 moles of carbon dioxide. Notice that these ratios, you got to be careful with whether you're dividing or whether you are multiplying. Step 5, determine the mass of carbon dioxide formed from the 1 kilogram of lithium hydroxide. We know how many moles of carbon dioxide we've got. We're going to multiply by the molar mass, 40 grams per mole. Our moles of carbon dioxide cancel out. We get 9.2 times 10 to the 2, or 920 grams of carbon dioxide. 920 grams of carbon dioxide will be absorbed by 1 kilogram of lithium hydroxide. So one of the examples that they always use for this when we're talking about stoichiometry is dealing with food.